thank you for the invitation. I'm a third-year PhD student working on breaking water waves, and I use FreeFem to make numerical simulation of those breaking waves. I will try to make my talk enjoyable for people which do not understand well the theory of water waves. So at first, I will start by talking about mathematical modeling of such waves. And as you will see, I used the Navier Stokes equation. And my idea is to see if by decreasing the viscosity, we are able to converge to Euler's equation solution. And to do so, I use FreeFem. And I will talk a lot about how I do this and show you some of the results I had during my PhD. So first, let's formulate the problem. So I use this kind of domain, which initially has no breaking whatsoever. So the interface is basically a graph, the graph of a function. And I define a Reynolds number using what's called the shallow water regime. The idea will be to let the Reynolds number tend to infinity, so the Reynolds number can be seen as the inverse of the viscosity. In this domain, I will solve the Navier Stokes equation. And about boundary condition, I don't want for the moment any boundary layer appearing on the bottom, so I use what's called the Navier condition, which basically says that I don't want the fluid to penetrate the boundary, and I want the stress on the tangential stress to vanish on the bottom. On the interface, I use what's called the stress-free boundary condition, which is well known. Basically, the stress tensor that must vanish on the interface. So in order to use FreeFem, I must put this into a weak formulation. So this is done here. The weak formulation is quite simple. So you have the material derivative here, the stress tensor, the viscosity here with the symmetric part of the gradient. The pressure is basically a Lagrange multiplier for the incompressibility condition. You also have the weak incompressibility condition here and the gravity. And this is what I will solve at each time iteration. What's quite new here is a Lagrangian advection scheme, which means that I represent the interface as a parametrized curve with S the parameter. And I want each point on the interface to move with the exact velocity of the fluid. So this is what this equation says. The initial condition is basically a linear wave with a finite amplitude. So this is a well-known analytical solution of the equations, but out of its regime of availability, because it's supposed to be a very small amplitude solution, and I use it with a high amplitude, with A, which will be about 0.5 times the depth H0 of the fluid. So now about using FreeFem to solve this problem, the idea will be to mesh only the water. I will neglect the air whatsoever, using a lot of triangles. I will come back to that later. So mostly I use 4,000 points on the interface, which leads to about 200,000 points, 200,000 triangles. And for the Navier Stokes problem, this leads to roughly 1 million unknowns, 1 million degrees of freedom. We will see that this number increases with the simulation. The mesh advection, since I want the interface particle to move with the fluid, but at the same time, I don't want the bottom particle to move at all. I use what's called the arbitrary Lagrangian Eulerian method, ALE. The idea is to solve this Laplace problem at each time iteration. So the Laplacian is 0. On the interface, I want W is the velocity of the mesh. I want W to be equal to the velocity of the fluid. And I want W to be 0 on the bottom so that the interface are advected like in a Lagrangian manner, while on the bottom, there is no advection at all. Of course, if I do that, so this is the time stepping scheme. So this is exactly what I solve at each time iteration in FreeFem. If I do that, I must subtract the velocity of the mesh in the advection term. So this is very well known for a long time. Also, I use a Crank-Nicolson scheme for the time step, but for the nonlinear part, because I don't want to use a nonlinear solver. So what I do is I only put the Crank-Nicolson in this value of u, and this one is treated explicitly. So that's about it. P2 elements for the velocity, P1 element for the pressure, and I put this in FreeFem, and it's very slow, obviously. So what I do is I use a domain decomposition method to parallelize the code. So I will try to use, I use basically a geometric multigrid preconditioner. So I decompose my domain, for instance, with 6 domains here, shown here, but it will be 24 to 48 subdomains during the simulation. And I use a geometric multigrid, which states that there is a fine level grid and other levels of coarser grids. And the basic idea of it, which was mentioned, which was talked about yesterday by Pierre Jolivet, it's basically that if I increase the number of subdomains, the information from domain to domain will take time to travel. So by using this kind of preconditioner, we increase the speed of transmission of the information from domain to domain, so that the number of iterations it takes to converge to the solution remains somewhat constant while increasing the number of subdomains. When doing so, here is some of the timing I had. So I did 5 numerical simulation with the Reynolds number ranging from 100 to 1 million. I increased a bit the number of interface points. And as you will see, the number of degrees of freedom will increase, because in order to capture the curvature of the interface, we will need more and more triangle in the near the tip of the wave, near the crest. I will show you the mesh afterward. So the number of triangle will increase from the start to the finish. And as you will see, by the end, we'll have at most 3,500,000 degrees of freedom for the largest simulation. Okay, about the convergence of the scheme converges very quickly. I mean, so I decrease the number of points by 2 each time, and you see that there is not much of a difference. But as I increase the Reynolds number to values that were never achieved before, the code becomes unstable quite quick. So that the main reason I need this many triangles, these many points, is that if I do not do so, the code will be unstable, even though it converges quite well. So of course, all this can be made quantitative using a certain distance, which I will talk about later. So about the results that we've been able to get with this method, here is an example of a simulation using a Reynolds number of 1 million, so the highest we've been able to get. And this is a breaking wave. Obviously, it looks like it. But what's interesting is to first show the triangles. So as you see, there are a lot of triangles near the tip. It might be a good idea to use an adapt mesh, a mesh adaptation in order to decrease the number of triangles, but still have enough precision near the tip. We're currently working on this with Georges back in the room. It might be a good idea also to use a mesh adaptation scheme to go in 3D, because with this method, it's already very slow, and I don't see any way to go in 3D without increasing the computational time to numbers that cannot be tractable. Of course, we have a very precise numerical method for the Navier Stokes equation, which allows to go to very high values of the Reynolds number. So what we can do is to compare our results with the solution of Euler's equation, which is the equation when you remove completely the viscosity. And this was done using another code that I won't present here because it was not made in FreeFem. As you know, any code that's not made in FreeFem doesn't need to exist. So it's basically a boundary integral code, just to mention it. And so this is the Reynolds equals infinity simulation shown here. And as you see, as I increase the time, so you don't see it quite well here, but it's very close to the Reynolds equals 10 to the power 5 and Reynolds equals 10 to the power 6 solution. And as the simulation increases, you see a gap, very small gap appearing. And we are able to go up to the splash. And as you see, I have to zoom in very clearly to see a small difference between the Reynolds equals 10 to the power 6 and Reynolds equals infinity solution. What this means is that it's a good idea to use Euler's equation in that case, because there is not much of a difference between the Navier Stokes and Euler's solution at these Reynolds number, which are typical Reynolds number in the theory of water waves. For instance, a wave, this corresponds to a wave of about 50 centimeter high. If I was interested in a breaking wave of like 1 meter high, the Reynolds number would be about 10 to the power 6 or 7 about this. So this is quite interesting result. What we can do is show where the viscous dissipation happens. And to see this, I take back my fluid mechanics book, and I take Navier Stokes, I multiply it by U, and I get this equation for the energy. And I see that the viscous dissipation related to the Reynolds number is only in the support of the vorticity omega. So what I do is I show and I compute and I show omega. And when I do so in yellow, this is omega equals 0 almost. And blue, this is omega equals not 0. So where there is a viscous dissipation happening, the solid black line was used to investigate the scaling of this boundary layer, which appeared. And I won't show it here. But what we see is that the boundary layer decreases as the square root of the inverse Reynolds number as the Reynolds number is increased, which is very typical in the theory of boundary layers. So this was the first time someone noticed this boundary layer, and we investigated it in a thorough manner. And we see that at the Reynolds equals 10 to the power 6, the boundary layer cannot be seen anymore, but it is present. It's only spread across one triangle. So it's a very small and also not very numerically resolved, but I could not increase the number of triangles anymore to have it. So I won't be able to do any better using this method. But it was interesting. We were able to see that the convergence of the Navier Stokes solution to the Euler solution is due to this size of the boundary layer, which decreases until it becomes infinitely located on the interface. But what happened when, instead of having a flat bottom, I now have a rectangular step? So to me, it's a rock, because I do math, so this is basically topologically a rock, but this is a rectangle. And now I use a Dirichlet boundary condition on the bottom, which before was not much of a problem there was only a boundary layer that appeared, but it was stable. This time, what we will see is that it's no longer stable. So now there is no breaking because I want many waves to pass above. And what I see when I show the vorticity is that vortices are emitted near the corners of the rectangle. And this was never really studied before, so we were quite amazed when we saw that. But for fluid mechanics, this is not much of a surprise. But most of the time when we study water waves, an assumption that we make is that the flow is irrotational. And I can assure you that it is not. The values of the vorticity in these vortices increases linearly with the Reynolds number, so that when we increase the Reynolds number, maybe you don't saw it because of the zoom thing, but the Reynolds number here is 10 to the power of 5. I could not achieve more higher Reynolds number because the vorticity would basically blow up, but it converges to like Dirac vortices when should we increase it even further. And the consequence of these vortices is that there is now a gap that appears between Euler's and Navier Stokes solution. So it's very small, and I should maybe get the simulations to go even further. But what we see is that the Navier Stokes solution now converges to something different than the Euler irrotational solution computed using the other code that I already mentioned. So it was quite surprising, and we don't know actually if this is a good idea to use the irrotationality assumption this time. Well, I can say that maybe not, but I don't know to which order of magnitude these vortices are actually present in the ocean in the nearshore analysis of the ocean. So I don't really know it. What I can do is first show you the convergence as we increase the Reynolds number once more. So you see that it seems to converge to Euler solution plus point vortices, but I don't know exactly when all these vortices emitted. And I don't even know if the flow maybe becomes turbulent at some point. What I can do is to smooth the edge using the well-known method of modifiers from the analysis of PDEs. And this time, with a very smooth edge, with a very low curvature, the boundary layer is stable. But as I increase the curvature, as I decrease the support of the modifier, there is a vortex that finally appears. So even in the case of an infinitely differentiable bottom, and even though this time it's still infinitely differentiable, there is a threshold of curvature in which the boundary layer becomes unstable, and these vortices appear. And this one was also even surprised some fluid mechanics people. So it was rather interesting thing. And I think my time it is done. So I thank you for your attention.
Question, comment, remark?
Yeah, so in the simulation that you show first, I think so you stop the simulation before the waves can fall on itself. So could you devise a scheme where you could using some using some level set method with background mesh, for instance, you could also capture what happens after the wave.
Yes, that's right. Because of the Lagrangian advection, and because I only mesh the water, once there is what's called the splash, so the moment the interface intersects itself, I don't know what to do. But this is the major flow of the method. This is due to the Lagrangian advection. Even the mathematical model breaks at this point.
I think we can discuss this.
Yes, but using level set method is an Eulerian method, and so it will change everything. Yeah,
You can combine the two. You can have a background mesh with your mesh as a sub mesh. And you use the level set method just to evolve the boundary, and then you remesh.
Yes, might be a good idea. We will discuss that.
Yes, you have a free boundary and you remove the mesh with the time. And I know that in the case, there is difficulty of the triangles that could reverse at some point. So my question is about when you refine the mesh, it's for accuracy, of course, but is it also for stability of the free surface?
Yes, in a sense. So I recompute the mesh every some time to times, basically because of these triangle elongation that appear, and I don't want them because it would break at
Okay,
some
so
point.
from time to time you compute a new mesh. And you,
Yes.
Okay. So how do you know when it's time to compute a new mesh?
I do it every time I do an output, and since I do many outputs, this seems like a good idea to do it at the same time. But I don't know. There might be cases where it's too soon, and I should recompute the mesh sooner.
One question, a very basic question. So you say more or less that you are limited by the time it takes and so on, but you use only, I would say, 48 cores. So why don't you go to bigger machines?
Yes, I should. That would be a good idea.
Question, when you showed the two real finite cores, it looked like they were not nested.
Yes, they are not. Otherwise, there won't, because otherwise the interface won't be as precise.
It would be interesting in the case where you have a block in the bottom to compare with a shallow water approximation.
Yeah, I would be too.